In this second video for chapter 7, we're going to start focusing in on proportions, and then we're going to move in and start talking about what does this 95% confidence level actually mean. So here we go. We're going to talk about a new parameter and a new statistic that we're going to be involved with, which is going to be p-hat. P-hat is going to be a sample proportion, which we use to make a prediction about a population proportion, p. Now, we don't use the Greek letter for p because that's already been reserved for the Greek letter pi. Now, anytime you have a proportion, it's going to be of the form x over n. This many people out of that many people. And you tend to hear the words out of when you're reading the problems regarding these type of problems. Okay, so I've got an example for you here, and it says if 108 families were sampled to see if they own a microwave and 102 responded yes, then the proportion of those who have a microwave, p-hat, will be 102 out of 108. And I want to make this comment here that both of these numbers are whole numbers. You cannot say 102.3 people say, yes, I have a microwave. It doesn't make sense to have 0.3 of a person. And you can't survey a fractional or decimal number of people either. So that 108 in the denominator also needs to be a whole number. Now, I call that to your attention because that will be a part of something later on that you're going to see where you have to sometimes massage your data and go back and kind of reconstruct what were those values of x and n. Now, in the next paragraph, I have the central limit theorem applied to the proportions. You are used to mu subscript x bar equals mu. Well, now we have mu subscript r p-hats is equal to mu, and the standard deviation of the population proportions has this new formula. Instead of p-hat times 1 minus p-hat, we're dividing it by square n, root of n, and you will see the p-hat times 1 minus p-hat showing up in a little bit, but bottom line is not going to be a calculation you're going to have to do much. When we are dealing with population proportions, there are a few assumptions. We're assuming we're taking random samples. We're assuming that the population that you're trying to make a claim about is at least 20 times bigger than the sample. And we assume that the items in the populations are of the two category nature, having and not having a particular attribute. Now, as far as this formula for the margin of error for an estimate of the proportion, here's the actual formula, which we'll never use because it's a lot easier to find the confidence interval and divide it by 2, as I showed you in the previous video when we were finding the margin of error for a confidence interval involving the mean. Now, just to remind you here, we are inside of our test menu on your calculator. In the first video, we spent a lot of time in option number 8 doing the t interval. Now we'll be at option A, which is the 1 proportion z interval. Even though it's pronounced or written as 1 prop z, I recommend you pronounce it as 1 proportion z interval, just to kind of train you. We're dealing with proportions when you're in that menu there. When you want to create an interval and you go into that choice number A, there's only 3 lines. You enter your x, you enter your n, and then you enter the confidence level as a decimal. So this would create a 95% confidence interval based on that 102 out of 108 that we saw just a moment ago dealing with the proportion who own microwaves. Now let's get into an actual problem here. Okay, it says studies are being performed to determine the percentage of the nation's 10 million asthmatics who are allergic to sulfites. In a recent survey, 38 out of 500 randomly selected US asthmatics were found to be allergic to sulfites. Notice it was 38 out of 500. That's the vocabulary that we tend to see when we are dealing with proportions. This one says determine a 98% confidence interval for the proportion, the true proportion P, I didn't put the word true in there, but I like to put that in there, of all US asthmatics who are allergic to sulfites. Well, just as with the means, when we use sample mean to make a prediction for the population mean, we're going to use our sample proportion P hat 38 out of 500 to be a prediction for the population proportion. Now, on my calculator, when it says create this confidence interval, well, here we go. I go into that one prop Z interval menu. I enter my 38 out of 500. I tell it that I want 0.95 for a 95% confidence interval, and out comes right here interval. Now it's in decimal form, and quite often when we're interpreting these things, we want to write these in terms of percentages. So we will be moving the decimal over, as you see here in a moment. So here is the phrasing we're going to use for our confidence interval wordings. We can be blank % confident. Well, we will know that that's going to be a 95% for this problem. That what? Well, this is going to be, and I'm going to word this out here, the true proportion of US asthmatics that are allergic to sulfites is between, and then you write these two numbers down. But notice I've moved the decimal 2 places to the right because it makes more sense to say the true proportion is between these two percentages instead of between these two decimals. Okay, so everything in green is what I basically filled in, and my units on these proportion problems are just going to be percent signs instead of units that we used back when we were dealing with the means. Okay, now determine the margin of error based on that confidence interval that we just created back in part A. Well, I took the width of that confidence interval. I took the high value minus the low value, and these were actually percentages. I'd all removed the decimals. I then found how wide it was. I divided by 2, and that told me my margin of error would be 2.323%. And this is exactly what we were doing in the first half of this chapter. Now we're going to keep this problem going here in just a little bit. Now we have a couple sample size formulas that we can use similar to what we used earlier. And if you go back into the other formula, we had N equals Z of alpha over 2 times sigma divided by E, and we went quantity squared. That was the sample size formula when we were dealing with an interval involving means. Now we're dealing with proportions, and we have 2 different formulas there. One, the first one, there's that P hat times 1 minus P hat I was talking about, which we use. And we do this when an estimate for P hat is known, when we have a guess as to what the proportion is. And then we use the second one that instead of the P hat times 1 minus P hat, we replace it with 0.25 out in front, rounded up to the next integer, when the estimate for P hat is unknown. So we basically, instead of having one formula like we had for the means, we've got 2 potential formulas here. Now, I've got a graph of P hat versus 1 minus P hat, okay? If I were to say, here's P hat on this axis, and then I would subtract it from 1 and multiply them together, that would be P hat times 1 minus P hat. The largest it can ever be on this graph is at a height of 0.25. That's why we put that right there in front, 0.25, because that will give us the largest sample size when we don't have a best guess for what P hat is. If we do have a guess for what P hat is, especially if it's a little bit further off to the side, then that leading coefficient that we multiply by is going to be a bit smaller, and it's going to reduce the sample size that we're going to be working with. Okay, all of that to say, now let's go and use it. So I'm still going back to this problem dealing with the US asthmatics. back here right above it on this page where we had 38 out of 500 asthmatics say, yes, I'm also allergic to sulfites. Now it says, find or create this sample size that will ensure of a margin of error of at most, basically that's 1%, but we always write these as a decimal when we're dealing with the proportion problems, for a 98% confidence interval without making a guess. I don't have a guess. That tells me, where's my pen? That tells me we're going to be using the bottom formula instead. P hat is unknown. Now, just like the sample size formula that we did earlier for the means, I've got to start working with alpha. They gave us 95% confidence, which means there's a 5% significance level that goes along with it because these two add up to 100%. Written as a decimal, the 5% significance would be our alpha is equal to 0.05, and then cutting it in half, we get the 0.025. Now it's time to come over here and use this formula, and I begin inside the parentheses. I begin with the inverse norm of alpha over 2. So inverse norm of alpha over 2. Notice it's the standard normal, and I use 0 and 1, and left is by default here. Okay, after that, I'm going to divide by E. Well, my error is at most 0.01, so I divided that by 0.01. That completed the fraction inside the parentheses. Now we know we've got to square it because of that quantity squared, and when I hit that square key on my calculator, I get a rather large number. And then I have out here in my formula the 0.25 to multiply by, and so when I multiply by 0.25, you get this value, and you always round up, so we get N equals 9,604 people we'd have to survey in order to be 95% confident that our estimate is at most 1% off. Okay, that's our margin of error. We don't want it to go over 1%. Okay, so that was using that second formula. And now it says, and actually I'm going to go for, let's go property. Find a 95% confidence interval for the true proportion for the sample size that we found back here in part D. And this time they're telling us the sample p hat is 0.071. We've done our surveying, out comes this p hat. So here we go. I'm going to go into my calculator and create this interval. Now, I'm just realizing we're going to have a little bit of a difficulty because when we go to do our one proportion z interval on our calculator, let me grab my calculator here. And unfortunately, I had turned it off, so I have to wait just a second here to get my calculator turned back on. But it's going to ask us to enter a x and an n. So my calculator is now turned on. I go in here to do a one proportion z interval. So I hit my stat button. I go to my tests, my tests, down to the one proportion z interval, which is choice A, a little bit lower down here. And when I hit enter, it asks for an x out of n. Well, we know in this problem that we don't have 20 out of 400. We know that our sample size is going to be 9,604. And they didn't give us x, but they did tell us 0.071. That's 7.1% of the 9,604. So I'm going to have to now multiply that by 9,604 like that. Now, when I do that and hit enter, it turns it into a number, but oopsie, that's not what I want because x can't be a decimal. But the closest whole number next to that, if I move up, is going to be 682. So I'm going to change that to 682 at that point. If you were to do x divided by n, it's going to be pretty darn close to that 0.071, which was actually a rounded value. And now we're able to actually go through and finish this calculation. And I hope that this matches exactly what I had over on the other screen. And it actually is a perfect match here. So I'm glad I actually did that one with you, because if I wasn't paying attention to what I was doing, you'd be going, oh boy, how do I do that? Okay, we're back to that comment here that I made at the start of this video that, and it's a couple screens back, both of these need to be whole numbers. And in this problem, they told us just, 7.1% were allergic to sulfites, and that's 7.1% of the 9,604 people. And you had to go backwards and generate what was that value of X. Okay, so you see there's a few extra steps in here occasionally. For part F, determine the margin of error for the estimate back in part E and compare it to the one we had back in part C. Okay, here we go. Margin of error, we find out how wide the interval is, and that's the first thing I did. I subtracted in the numerator there, divided it by 2, and it basically came out to be about 0.5% was the margin of error, a little bit more than 0.5%. Well, let's compare that to the margin of error back in part C. If I go back to part C, notice how our margin of error was 2.3%. Well, now our margin's a whole lot smaller because we wanted to make sure that we are under 1%, because that was where we had right there, but also because we have a much larger sample size this time. That's going to generate that for us. Okay, it is smaller. It's far below 1%. Which is what we did in part D, but I really was looking at part C. It's based on the larger sample. We know we can be much more confident. There's going to be much less error. Moving on to this next example. 35% of adults in America eat pizza at least once per week. Where that came, no clue. A random sample of 250 adults in a medium-sized college town were surveyed, and it was found that 110 eat pizza at least once a week. Estimate the true proportion of American adults who eat pizza at least once a week with 90% confidence, and comment on other results. Okay, our first guess is let's create a point estimate. Our point estimate is going to be 110 out of 250. There's my X and my N, and based upon that, I would then be able to go in here and say, okay, here's my X, here's my N, here's my confidence level of 0.9 that I want. It will generate this interval, and our comment on this would be, we can be 90% confident that the true mean, sorry, not the true mean, the true proportion of adult Americans, or at least in that city, who eat pizza at least once a week is between 38.836% and 49.164%. Okay, so I know you might have to pause that and rewind it to get those words. I said, we can be, okay, there's that wording, we can be 90% confident that what? That the percentage of adults in America that eat pizza at least once a week is between these two percentages. Okay, next example. A recent study indicated that 29% of the 100 women over age 55 in a study were widows. Okay, 29% of the 100. Well, I'm glad that there were 100 people in the survey, because 29 out of a 100, I knew that this was going to be 29 and 100 as X and N, and I didn't have to do any other fancy mathematical calculations. This time they're asking us again, how large a sample must we take in order to be 90% confident that the estimate is within, oh boy, we want to be within 5%. So that 0.05 that we have here, that's the margin of error we're willing to live with. We've got our confidence level, and we have a p-hat. Since we have a p-hat, we're going to use this first formula here instead. We've got this estimate that we're using. We don't have the population proportion. We're trying to make a prediction about that. So just as before, we start with our confidence level, which is 90%. I say, okay, 90% goes with, of confidence goes with 10% significance. 10% written as a decimal is 0.10, that's my alpha. Cut that in half and I get 0.05. Now I'm going to move into this formula here, and I'm going to start with that numerator. And here are the numbers when I plug it in. I'm going to have p-hat and 1 minus p-hat. There is my 0.29 and my 1 minus 0.29. Then I'm going to do inverse norm of the 5%. That's the same 5% alpha over 2 we mentioned here at the left. And my margin of error written in decimal form, 0.05 is what we want there. So that's what's going into the calculator. Now I do this in multiple steps. Instead, I'm going to start with my inverse norm on that top row. Just like before, it's under the standard normal curve with mean of 0 and standard deviation of 1 and the area to the left. Then I'm going to finish that fraction, divide by the 0.05. Now that fraction is going to get squared. There we have it. And then I have these two numbers out in front that need to be multiplied by, and that's what I did. I times it by 0.29 and then 1 minus 0.29. And then when you get an answer, you always round up to the next largest whole number. Now, how would you do this if no estimate was available to you? So here we have the problem where you're going to use the one with the 0.25 in front. Every single beginning step is going to be the same. The only thing that's going to change is down here at the bottom row. Notice the 1082 is the same in the first 3 steps. Instead of multiplying by p-hat and 1 minus p-hat, I'm multiplying, or we are multiplying by 0.25. So this time, the sample size is going to be n equals 271. In other words, we're going to have to sample another 48 people just because we didn't have an initial estimate for what the proportion would be. Now, what is a takeaway for you guys? If you are ever going to do a survey, always do a pre-survey in advance to get an estimate of what the true proportion is going to be. And if you get that pre-estimate, then you can cut down on the sample that you would have to do later in order to be a certain level confident. And that could actually save you a lot of money, especially if it's a costly type of personal interview that you were performing. Okay, so that's the sample size formula. And we've practiced learning how to do the 1 proportion Z test and find 1 proportion Z intervals. Okay, now of an activity that if we were in class, this would be your favorite activity of the semester, because I'd be bringing Hershey's Kisses into the classroom. We all know that when you flip a coin, the probability of a heads and a tails is each going to be 1/2. However, you don't know when you flip a Hershey's Kiss, whether it's going to land on the flat round base or whether it's going to be tilted with that point end kind of down onto the table. And that's just something we can't tell. It's not a standard value. And the only way we could actually get that true value would be to buy a whole bunch of Hershey's Kisses and do a whole bunch of tossing and do a large number of trials until we could get a rather accurate guess as to what that probability would be. So what I would do if we were in the classroom is I'd probably give everybody about 10 Hershey's Kisses. And I'd say, okay, here's a little cup to shake them in and toss them out on the table. And I would ask you the following question. I would say, okay, I want you to toss 100 Hershey's Kisses. So I'd give you 10, and you would do 10 at a time, count how many land on the base, 10 at a time again, and then until you got 100 of them. And out of the 100, I would ask you how many of them land on their base. Now, here's what's interesting. Not everybody's gonna get the same result. You guys know if you flip a coin 100 times, not everybody's going to get 50 heads and 50 tails. You're going to get 52s, you're going to get 47s, you're going to get all sorts of numbers, somewhat centered around 50, because that's the true mean number of, or what we would expect, a proportion. But in this case, we don't know what that answer is. So I'm going to just pretend I'm one student here, and I say, okay, I did this 100 times, and whoopsie, I got an answer here of, let me switch this a little bit, turn it, this is not letting me move it. Well, I'm going to do it this way. I'm going to pretend that we got an answer of 38. 38 out of my 100 times, it landed on its base. Okay, well, that's what one person got, and everybody in the classroom would, not everybody would have a different number. A few people might have repeats, but we're going to get a lot of different responses in the classroom. Was there a right and was there a wrong? No, it just depends on the way it happened. So after everyone's done that, I then say, okay, now based on your results, I want you to find a 95% confidence interval for the true proportion of Hershey's Kisses that will land on the base. You don't know what the true proportion is. This is an unknown, uncharted territory here. So person number one, who had the guess of 38, is going to go to their calculator, and they're going to say, okay, here we go, a 1 proportion Z interval. I had 38 out of 100 of my flips land on the base. And I'm going to create a 95% confidence interval, and out comes this beautiful interval. So that person says, I'm 95% confident that the true proportion of the number of times it's supposed to land on the base should be 28.48% up to 47.513%. That's my estimate, and I'm going to stick with it. Okay, but someone else in the class goes, but wait, no. I didn't get 38 landing on their base. And they say instead, let me see what number I used. That person says it landed on the base 33 times out of 100. And my interval doesn't go from 28% to 47, it goes from 23 to 42-ish. I've got a different interval than you do. Now, is one of them right and one of them wrong? Well, they're both estimates. Neither right nor wrong yet. They're making predictions. And in statistics, we attach a probability to it. We said we're 95% confident. Now, in our classroom, let's pretend we had 30 people in the room that day, and we have 30 different responses coming in. I would have people up at the board, and we would draw a picture similar to what I'm going to have on the next screen. Okay, what I do is I put a numerical scale on the board, and I say, everyone place a dot where your number is in terms of how many times did it land on the base. So if you had 38%, that's going to be a little bit to the left of 0.4 down here. And let's pretend this one that I'm pointing at is at 38%. I'm just pretending. That would be that. And then I drew an interval, which you see in green, around it, where we say from here to here. This is where I think the true proportion is, that when you flip a Hershey's Kiss, it should land on its base. What's the probability? Now, I happen to know, and we have a whole bunch of these green little intervals drawn on the board. Then I would come back and say, you know what? I know the true probability. The true probability, and this is because it's been done in a whole lot of classrooms, is 35%. That's the black bar going down the center there. Now, almost all of these green interviews, or all the green ones, contained 35%. The 3 that are in red didn't. In this case, all 3 were a little bit on the high side. Their estimate for the true proportion was a little bit high. Okay, now I got something covered up, and let's talk about what this 95% confidence interval means. Okay, now I've actually done this a whole bunch of times. There was just one sample, and I've done a computer simulation of this 4 more times. And basically the first time, 97 out of 100 times, the true proportion, 35%, was included in 97 out of the 100 intervals. You see the 3 in red are the 3 where it didn't capture the true proportion of 35%. But we didn't say we were always going to be right. We were saying we were going to be right 95% of the time. And in this first case, we were right 97% of the time. This next one, 6 of those are highlighted in red. So 94% of the time, we were successful in capturing what I'm telling you is the true proportion of 38%. The next one, 96 of the 100 were successful. The next one after that, perfectly 95 of the 100 perfectly, correctly captured the 38% in the interval, and then it dropped down to 94%. So if I were to keep a running total of all of these together, 1, 2, 3, 4, 5 of them, we're at a 500. I would tell you that we're at 476 out of 500. And if you combine all of them together, we're kind of at a running total here of 95.2% of the time we were successful in predicting the true proportion, which I am told is 35%. This activity has been done in a lot of classrooms across the nation, and they've gathered this data, and they've said, based on this large number of trials, the true proportion is 35%, or probably pretty close to it. It might be a rounded number. But bottom line, we are trying to do this. Okay, now let me summarize what this means on this next screen. And I am going to do some reading because I think it's very well worded. Okay, you're used to this picture here. You know the true proportion is 35%. You don't know that when you're making your guesses. But I wanted to talk, what does this "we can be 95% confident that" actually mean? So here we go. Let's read this at the right. When we construct a confidence interval based upon our data, we are only getting a look at one of these confidence intervals, which we create from the data. Just like we did 2 screens back when we said, oh, 38 kisses, 38 out of 100, here's my interval. We only get to see that one interval. We don't see any of the other intervals from our classmates, nor do we see that black vertical line, which represents the true value of mu or p, depending on whether we're dealing with means or proportions. Therefore, we cannot be sure whether our confidence interval actually covers mu or p, or whether we were one of the unlucky enough ones to get one of the unsuccessful ones, which are the ones I've got colored here in red that don't cover the true proportion. A single confidence interval is constructed by a method that succeeds in capturing the true mean or proportion 95% of the time. Now, the method we're using is the formula that's programmed into our calculator. Here's where we're really getting at. Rather than describing the success of any particular interval, hey, my interval got it, okay, in capturing the true mean or proportion, the confidence level describes the success rate for the method used to construct a confidence interval, okay? In other words, in the long run, we will be successful in capturing the true mean or proportion in our confidence interval 95% of the time. Okay, it's not about a specific, but 95% of the time in general, we will be successful in our prediction. Now, before I close off this video, I want to go way back to the beginning of the confidence intervals at the start of actually the previous chapter. A previous video, I should say. When we did our first confidence interval in section 7.3, I said, here's this paragraph we're going to go back and look at. Okay, this confidence level, it's not just this is how sure we are, even though that's the way it sounds, okay? It says, if we were to draw many samples and use each one to construct a confidence interval, like we did in that picture a little bit ago, then in the long run, the percentage of confidence intervals that cover the true value of the mean of the proportion would be equal to that confidence level. Now, we're just going to keep saying we can be 90% confident that or 95% confident that. But I wanted in this last example to really illustrate for you what that phrase actually means.